One of the most complicated periodic trends to explain fully is ionisation energy, or first ionisation energy to be more specific. It's covered very, very well in the SciPad on pages 23 and 24, with some good examples on pages 25 through to 27. It's also explained quite well in Education Perfect, but I do think the explanations in the SciPad are a bit better. The first thing we need to be able to do is to define ionisation energy, and that's actually quite tricky. So I always start my definition with an equation like this for any generic atom. Ionisation energy is the amount of energy required, so it's got a positive delta H, the amount of energy required to remove 1 mole of electrons from an atom in its gaseous state. Now, why is that important? Well, the amount of energy required to remove those electrons gives us an idea of its atomic structure. We can also do a second ionisation energy, so remove the second electron as well. Third will be the third electron and so on. And when these numbers increase dramatically, they suggest to us that there's something particular about the atomic structure. Maybe we've removed an entire energy level's electrons, and now the electrons are much closer to the nucleus, so harder to remove. The general trend for first ionisation energy is this. It increases as we go across a period, and it decreases as we go down a group. Now, knowing that trend is quite easy because it's very, very similar to it's the same as atomic radius. And there's a reason for this. We have to consider a lot of factors, but the very first one we do consider is atomic radius. The closer those outermost electrons are to the nucleus, the more difficult it will be to remove them. So the more energy would be required. And of course, the atoms on the far right have got smaller radii than the ones on the far left. So that makes sense. But when you get across to, for example, nitrogen, oxygen, fluorine, their radii are very similar because there's also, as well as an increased nuclear charge, there's also electric repulsion of the electrons in the same shell or energy level. So their atomic radius doesn't change much, but their ionisation energy does continue to increase at a very measurable amount. And that's because of an increased effective nuclear charge. So remember, that's taking into consideration 1, the number of protons, and 2, the amount of shielding. So effective nuclear charge is the key thing here, not just nuclear charge. But again, going across a period, that trend makes sense. And again, going down a group, that makes sense as well because you get an increased amount of shielding, so the atomic radius has got bigger and the effect of the nuclear charge is actually dampened by the shielding. Then you get the next two, and these are the really hard ones to understand or to get your head around as a new concept. First of all, a filled sublevel. So for example, 2s is a sublevel, 2p is a sublevel, and so on. You have to consider that as a factor. Boron has got a lower ionisation energy than beryllium, even though it should have a higher one because across the period they increase. And the reason for that is that the 2p sublevel is a little bit higher than the 2s for energy. So therefore it's actually a little bit further away from the nucleus. But with the increased nuclear charge, it gets held in quite tightly. So what we find is because of this 2p1, because there are electrons in the 2p orbital, this one is a lot easier to remove than one of these 2s electrons from beryllium. So beryllium has a much higher ionisation, well not much, but it has a higher ionisation energy than boron, even though boron has a smaller radius and a higher effective nuclear charge. The 2p electron is easier to remove because the 2p orbital has a slightly higher energy and does go a bit further away from the nucleus. Now, if all of that is the same, then we go to our fourth thing, which is maximum spin. So I've used nitrogen and oxygen as my examples here. Nitrogen has a higher ionisation energy than oxygen, and you'd expect it to be the other way around, but it's not. So why is that? For filled sublevels, it's the same. They're both partially filled 2p, so that's the same. Their effective nuclear charge, well, oxygen's is actually higher, so surely it should have a higher ionisation energy. The atomic radius of these two is almost identical. It's pretty much the same. So why is it easier to remove an electron from oxygen than it is from nitrogen? It seems quite counterintuitive, quite back to front. And the reason is here. In nitrogen, the 2p orbital has maximum spin. So hopefully remember that from our learning about atomic structure and electron configurations. All of these electrons spin the same way on different p orbitals in the p sublevel. In oxygen, one of these orbitals has got the electrons paired up, and that means there's a bit more electric repulsion between these two electrons, which makes it easier to remove that electron there. So, to recap, you need to know the definition. It's easiest to write it as an equation and then try to put it in words. You need to know the trend, and it's a general trend. There are exceptions. You need to know the factors that influence those trends and those exceptions, and they are atomic radius, which that trend follows beautifully. Effective nuclear charge, again, that trend follows that beautifully. But then you get the exceptions and you have to explain them. Check if they've got a filled sublevel or not. If it's a filled sublevel, it will hold on to those electrons a little bit more tightly. If it has a partially filled sublevel, then that's going to be a little bit easier to remove than the electron before it in the periodic table. If all of that is the same, like in nitrogen and oxygen, check for maximum spin, because that is an indication of electric repulsion. Maximum spin has less electric repulsion than, for example, oxygen, where it has one of them paired up, and so therefore the energy required to remove an electron from oxygen is lower than you'd expect, and therefore lower than nitrogen.